So working our way down the convergence test, our first test was to see if you could identify the series as geometric. And so if we're looking at our flow chart up here, we're trying to determine, is our series geometric? If so, then we can look at the R value and determine, is that R value between -1 and 1? If the answer is yes, then your series converges. If it's not, then you know your series diverges. If you cannot establish it as a geometric series, then the next test is to perform the divergence test. And then the divergence test simply says, evaluate the expression that's in your series, and if the limit as k approaches infinity does not equal 0, then we know that our series diverges and we're done. But then looking at our flow chart, if it's not geometric, and then if we establish that the limit as k approaches infinity of our rule does equal 0, then we need some more tests. And so the test we are going to use is something called the p-series test. And this may seem brand new, but it's actually very similar to one of the rules that we learned in chapter 2 relating to improper integrals. And so we determined, I'll go ahead and write it down here and then we'll erase it. We said that if you have an improper integral, so an improper integral meaning you're starting from a lower value of 1 or some other value, and basically you're including infinity in either the upper or the lower. And so if we look at 1 over x to the p dx, and we determine that in this form, if p was greater than 1, then our series converged. And if for some reason p was less than or equal to 1, then we know, I should say series, excuse me, integral, we know the integral diverged. And so what did it mean to have an improper integral that converged? We knew that the graph, if you evaluated it in this instance from 1 to infinity, that this particular area, even though it has an infinite right boundary, that if it's getting small enough, fast enough, then this area models finite behavior. And so using that same idea, we're now going to use something called the p-series test, which essentially works the same way. And it says if you have a series in the form x equals 1 to infinity of 1 over x to the p, as long as p is greater than 1, then our series converges. Now, what does it converge to? We'll address that at a different time. And so looking at our first example here, so example 3 for p-series test says determine whether the series below converges or diverges. And so this one is a little different from examples 1 and 2. Where in example 1, it said show that the series converges. So if we knew that it converged, you just had to prove it. And then in example 2, it said show that the series diverges. Again, we know it diverges, you just had to prove it. Here it's a little more open-ended where they're asking you to evaluate whether the series converges or diverges. And so the way we do that is the same way we tackled this first question for geometric, and that is if you've got a single term on the bottom, you're allowed to split the fraction. And so we're going to do that as well here. And so this series we are going to rewrite as k equals 1 to infinity, and we're going to split it into 4 over k squared plus, and we're going to go ahead and write it as a separate series of the square root of k over k squared. And so the idea here is we're going to look at each of these individually, and if we can prove that both of them converge, then we know the sum of the two converges as well. And so the first value we find here, we've got 4 over k squared. Now it seems like we've got an issue because according to the rule, we have a 1 up top, and here we have a 4. But we're going to find that series act a lot like integrals. And so one of the properties you can do with a series is you can actually pull this constant out front. So if I ask you to find the sum of the infinite series from k equals 1 to infinity of 4 over k squared, you can actually rewrite that as 4 times the sum from k equals 1 to infinity of 1 over k squared. And if I look at this particular series, I notice it's 1 over k squared. So the 2 ends up being p. That value 2 is greater than 1. Therefore, by the p-series test, I know that this particular series converges. Now, if you wonder, what are we doing with the 4? Well, if this part of the series converges to a number, all the 4 is doing is multiplying whatever value that is times 4. And so either way, it's not going to change the fact that the series converges. And then over here, we've got another issue where I don't have a 1 on top. I actually have a power of k. Well, if we remember our rules of exponents, we've got k to the 1/2 over k to the second. And so that allows me to rewrite this particular series as the sum from k equals 1 to infinity of 1 over k to the 3/2. And similar to what we just did there, we now have a 1 on top. The value for p is 3/2. 3/2 is greater than 1. Therefore, this particular series also converges. And so what does that tell me about the original series? It tells me that the original series also converges because the two parts that it split into also converge. Now, what would happen if we looked at this series and we found out that this part converged, but this part over here diverged? Then the entire series would diverge. So you need both parts of this to converge for your series to converge. Otherwise, you're going to have a value from this, but then the whole idea behind the series diverging is its values, or the sum, would approach infinity. So if you have infinity plus some value here, the entire thing is going to diverge. So it's very important that you prove both parts of it converge.